Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lectures, we have seen Z transform as well as inverse Z transform and seen its equations also. Now there might be some cases in which use of these equations might be difficult or rather time consuming. So in such cases, the properties of Z transform comes to our savior. So let us look at some of the properties of Z transform. But before that, let me list some of the important notations that I would be using while explaining or rather listing those properties. So if we have a discrete time signal x of n, then its Z transform will be indicated by x of z and its region of convergence would be R. And if we have to consider two discrete time signals, while explaining some properties, at that time we'll have first one as x1 of n with Z transform as x1 of z and region of convergence as R1, and the second signal will be x2 of n with Z transform as x2 of z and region of convergence as R2. So let's start with the properties. The first property which we are going to look is the linearity property, in which we have two discrete time signals x1 of n and x2 of n, and if we have a linear combination of those two signals, that is a into x1 of n plus b into x2 of n, then the linearity property says that its Z transform will be also a linear combination of the individual Z transform with the same scaling factors, that is a into x1 of z plus b into x2 of z. And here the new region of convergence would be at least R1 intersection R2, or rather the overlap between the region of convergence of the individual signals. Let us move on to second property, which is the time shift property. It states that if we shift the discrete time signal x of n by a factor n naught, then the Z transform of the resultant signal is the Z transform of the original signal x of n multiplied by the factor of z to the power minus n naught. And the region of convergence now becomes the original region of convergence plus possibility of poles at z equal to 0 if this n naught factor is greater than 0, or possibility of poles at z equal to infinity if this n naught is less than 0. The third property is the time reversal property. Which says that if we flip the discrete time signal along the time axis, that is x of minus n, then its Z transform is given by x of z inverse. And if z belongs to the region of convergence of the original signal x of n, then the region of convergence of this new signal, that is the flipped version, is given as z inverse. Let us move on to the fourth property, which is the time scaling property. It states that if we scale the time axis by a real factor dn, that is x of dn has a Z transform as x of z to the power 1 by d, and the region of convergence becomes z to the power d, where this z is a part of R, which is the region of convergence of the original signal x of n. The fifth property is one of the most important property, and that is the time convolution property. It states that the Z transform of the convolution of two signals, that is x1 of n convolved with x2 of n, results into x1 of z into x2 of z. So convolution in time domain results into multiplication in z domain. Now this property is important when we are analyzing systems. For example, if we have an LTI system, we know that it is characterized by its impulse response h of n. So suppose this is my LTI system with impulse response as h of n, and let x of n be its input and output be as y of n. And this output can be calculated using the convolution sum given by x of n convolved with the impulse response h of n. Now if we take the z transform of y of n, we have y of z is equal to x of z into h of z. Using this time convolution property, we have x of z into h of z. Therefore, the z transform of the impulse response can be calculated as y of z, that is the z transform of output, upon x of z, that is the z transform of input. Now many times we don't have the equation of this impulse response directly, and we know what is the output or what is the response of the system for a particular type of input, and hence in such cases we can analyze the system or get the impulse response very easily by just dividing the z transform of the respective output and input. So that becomes very useful property here. Let's move on to the next property, which is the time multiplication property. Which states that if we have multiplication of two signals, its Z transform is a complex convolution given by 1 upon 2 pi j integral over a contour of C x1 of nu into x2 of z by nu into nu inverse d nu. The next property is conjugation property. Which states that the Z transform of the complex conjugate of the signal, here the complex conjugate the Z transform of the complex conjugate of the signal is again complex conjugate of the Z transform, but we have the conjugate of that Z also, and the region of convergence remains same. Now in this time multiplication property, the region of convergence is the intersection, and similarly in this time convolution property also, the ROC is the intersection of the two individual ROCs. Let us move on to the next property, that is scaling in frequency or the Z domain. So if we scale the Z transform by a factor of A, it results in multiplication or scaling by a factor of A to the power n to the time domain. And in this case, the region of convergence is mod of Z into A, where this Z belongs to the region of convergence of the original signal. The next property is the first difference property. Which states that the Z transform of x of n minus x of n minus 1 is given by x of z, that is Z transform of x of n, scaled by 1 minus Z inverse. Now this is nothing but a combination of time shift and linearity property. We know that the Z transform of x of n is x of z, and the shifted version has a Z transform of x of z into z to the power of minus of shift, that is minus 1. And if we apply linearity property to this and take this x of z common, we get this back, that is x of z into 1 minus z inverse. And this ROC of the new Z transform is the ROC of original signal intersection of mod of z greater than 0. We can observe that there is a pole at z equal to 0. So because of this, we have intersection of mod of z greater than 0. Let us look at the next property, that is running sum property. Which states that the Z transform of summation L running from minus infinity to n x of L is given by x of z upon 1 minus z inverse, and its region of convergence is given by the region of convergence of the original signal, that is x of n intersection mod of z greater than 1. The next property is differentiation in z domain. Now suppose I multiply a signal by n, that is we have n into x of n, then its z transform will be given by minus of z into d dz of x of z. Means multiplication by n in the time domain will result into differentiation in the z domain, and the ROC, that is the region of convergence, remains same. Now we'll look at two important theorems for causal systems. The first one is initial value theorem. This theorem allows us to find the initial value, that is at time instant n equal to 0, even if we have only its z domain representation. So to find the initial value, that is limit n tending to 0 x of n, which is the initial value, it can be found by limit z tending to infinity x of z. And the second one is the final value theorem. In which limit z tending to infinity x of n can be calculated as limit z tending to 1 z minus 1 into x of z. Now these two theorems are for causal systems. and they allow us to know the value at the initial as well as final time instant, even if we have only its Z domain representation. In this lecture, we have seen various properties of Z transform which become very useful if we have complicated expressions in the time domain, and in Z domain if we need to come back to the time domain. So I'll urge the viewers to just try and prove these properties, as it would be very interesting and will give more insights about these properties. Let's stop here. Thank you.